I will be doing a step-by-step tutorial on how to solve problem 21-24 as my final project for ME21. Here's the problem. A 15 kilogram circular disk spins about its axle with a constant angular velocity of 10 radians per second. Simultaneously, the yoke is rotating with a constant angular velocity of 5 radians per second. We are asked to determine the angular momentum of the disk about its center of mass, O, and its total kinetic energy. Here are the steps we'll be taking. We will first start by defining our initial known and unknown variables. We will then use these known variables to solve for the mass moment of inertia of the disk, then the angular velocity in each of the x, y, and z directions. Then we will solve for the total angular momentum and kinetic energy. First, let's write down what we know. We know that the mass of the disk is 15 kilograms, and the illustration on the right shows that the radius of the disk is 150 millimeters, which is 0.15 meters. We are also given angular velocities omega 1 and omega 2. Notice how omega 1 is set to be negative. This is because of the right-hand rule. If you point your thumb in the positive y direction, your fingers will curl in the positive direction. Since omega 1 is spinning in the opposite direction, it is negative. Omega 2 is positive by that same logic. I am marking these with a J and K to keep track of which axes they refer to. J refers to the y-axis and K refers to the z-axis. At the bottom are our two unknowns, the net angular momentum and the kinetic energy. Let's store these variables on the left side of the screen. Now we will find the mass moment of inertia for our disk. The equations for the mass moment of inertia for a disk are standardized and change depending on the axis. It is identical for the x and z axis because the disk is completely symmetrical about the y-axis. This means that you could spin the disk around as much as you want, but the x and z axis will remain unchanged. Using this equation, which is 1/4 mr squared, we can plug in our values from the left to determine the mass moment of inertia for the x and z axis. The mass moment of inertia for the y-axis is just the sum of the previous two and can be generalized with the expression 1/2 mr squared. Once again, we can plug in our values to solve. I'm going to store these values on the left so that we can refer to them later. Now we're going to find the net angular velocity. Since this disk is perfectly symmetrical about all three axes, we can assume that all of the axial mass moments of inertia are zero, since all the axes pass through the center of mass. This makes finding the net angular velocity so much easier, since we can just ignore the moments of inertia and add up the omega values we were given. This is where the J and K notations we wrote earlier came in handy. There is no I value, so the angular velocity about the x-axis, which is written here as omega x, is 0. Omega y is equal to the given omega 1 at negative 10 radians per second, and omega z is equal to the given omega 2 at 5 radians per second. These values will help us in the next step. Now we're finally going to solve for the angular momentum. Angular momentum, represented by h in this general equation, is the product of the moment of inertia and the angular velocity. We can use these values that we have now on the left to solve for the angular momentum about the x, y, and z axes. Then, since the net angular momentum is just the sum of all of its components, we can add them all up in vector form to get our solution here at the bottom. Let's store this and move on to the final part. All that's left for us to do now is to solve for the total kinetic energy of the system. Kinetic energy is the energy stored by motion, and in linear systems it is represented by 1/2 mv squared, where m is the mass of the object and v is its current velocity. However, since we're dealing with radial motion, we will need to use the radiant variant of this equation. Here kinetic energy is represented by 1/2 I omega squared, where I is the moment of inertia and omega is angular velocity. Like with angular momentum before, we can break kinetic energy into its x and y and z components. And once again, it's just a matter of plugging in our variables that we've already solved for on the left. So there we have it. The net angular momentum of the disk is negative 1.69 kilogram meters squared per second in the y direction, and 0.42 kilogram meters squared per second in the z direction. The net kinetic energy of the disk is 9.49 joules. Thank you for watching.